Hello again everyone, I just wanted to paste a quick correction to the last video that I did. I think I've mentioned before that I'm in contact with a chap called Dave who he's retired now, but he used to work for a significant or well-known amplifier manufacturer, and he's been helping me along every step of the way with this project. I can't thank him enough really, because as I've said before, I just never would have even got this far without his help. I don't think he's actually seen the videos that I posted so far up until the last one, and I showed it to him, and I think he watched that back with some of the other videos, and he turned around and said to me, Dave, to be quite honest with you, what you did in that last video, or what you said in that last video, complete nonsense, although I think he phrased it slightly differently, and I'll tell you why. It's not that everything I said in the video was wrong, but I did fundamentally get one thing wrong or misunderstand one of the components, and I want to explain that to you now. It's to do with this whole business of the volume control acting as a high pass filter. If you don't know what I'm talking about, go back and watch the previous video in this series and you'll see exactly what I mean, and you'll see the schematic for my current amplifier. If you're familiar with amplifier schematics, you'll know what a typical basic preamp looks like, but either way, I'm just going to kind of jump in by saying that this is a coupling capacitor coming from the first gain stage. So you've got your first valve or first triode over here, your audio signal comes out into the coupling capacitor, if that's how you want to visualize it anyway, and you come down from here and you've got your volume pot. This is the symbol for the volume pot, connected down to ground, and then the other output from the volume pot going to the grid of the next valve, or the next triode I should say. And that's kind of like what the interstage coupling between the two halves of the preamp valve look like, and this is where our volume pot sits. Now, what I said was that this capacitor and this resistor work together to form a high pass filter whereby the bass frequencies below a certain threshold are effectively cut. To some extent that's true, but the point that I made that was incorrect was that when this volume control is altered, it changes the frequency at which that filter cuts off, and I'll show you why. So, a basic high pass filter looks like this. Well, actually, if we just draw the capacitor on its own, the capacitor on its own will actually act as a filter just by itself. It has an inherent cutoff frequency which is typically very low. In the values of capacitor that we use, it could be well below the audible range, or if you're clever about it, you might have it at about 60 Hertz so that it cuts out the hum from your electricity supply, somewhere around that range. But the point is, if you introduce a resistor to ground, so if this is our ground rail, we put a resistor in here, adding a connection into ground, because if you imagine there's no resistor there's effectively infinite resistance to ground. As we decrease the resistance to ground, the point at which this thing starts cutting off gets higher and higher and higher in terms of frequency, until eventually everything's cut off, I guess. If there's no resistance, no signal will flow. So for example, if we had a 1 meg resistor here, it'll start cutting off at one frequency, we'll say for the arguments of 100 Hertz, but if we change that down to 500k, that might then become 200 Hertz, and so on. We don't need to do the math right now, it's still valid what I posted in the previous video. The point I made was though that we've effectively created this by putting our volume pot in here, and we've created a high pass filter. And that is actually true, we have created a high pass filter, but as I said, it was wrong to say that when the volume control is turned, the value or the frequency at which the high pass filter will cut off will change, or at least it won't change significantly. And here's why. I was effectively thinking about potentiometers in the wrong way, or at least thinking about the way that they're wired up in the wrong way. So this is what a potentiometer can be visualized like. You've got an input and an output again. And you've got a band of material which is effectively a resistor. The resistive material, drawn that too big, never mind. This is a band of resistive material between the input and the output. But what you also have is a second output connected to the little rotary bit in the middle. It might not actually be laid out like this, but this is the best way to visualize it. So you've got an output here as well. And what this has is a connector which, when you turn the knob on the potentiometer, it will sweep across this resistive material. And what that means is when you turn the knob, it changes the amount of material that the input signal has to pass through before it can exit via this output. So if you have the knob all the way to the left, there's practically no material to pass through, and if you have the knob all the way to the right, it has to go all the way around here before it can get to the output. That means this output effectively has variable resistance. In contrast to that, this output has a fixed resistance because the signal always has to come through the entirety of the resistor before it exits. So in the context of our amplifier, this is actually the input where the signal comes from. But this is the output in terms of the one going to the grid of the next amplification stage. And the out is actually going to ground. What does that mean? Well, that means in the context of this diagram up here, the value between this capacitor and ground always stays the same. Only the resistance between the grid and, well, the capacitor and ground changes. So if it is the value of this resistor which sets the frequency that this cuts off at, that's never actually going to change. So if this is, for the sake of argument, a 1 megohm pot, that output is always going to have 1 meg of resistance between there and there. So that frequency will stay the same, and the volume to the grid will always change, but without altering the frequency. That's the mistake I made. Hopefully that corrects a few things for people. Let me just redraw that for you, just to kind of drive the point home. So, as I already said, we might have, in the context of the amplifier, we have our first gain stage. And that will go up there, typically to a resistor, not that we care about it at this point. And that will come across to a coupling capacitor. Only our AC signal will go through the coupling capacitor. Comes down to our volume pot. This is ground. And we've got the connection into the grid of the next valve. So the path of our audio signal, as I described in the last video, comes into this valve, gets amplified, comes out the top. Only the AC signal crosses the capacitor and comes down to here. And then, if you remember how the variable resistor works, if I draw it on its side this time so it matches, we've got the in, which is here, passes through the resistor to ground, which is here. So this variable resistor is this variable resistor here, and the value here remains constant between the input and ground. So that means the value between here and here remains constant, and the output to the grid is here. That is what varies in resistance. So as far as this coupling capacitor is concerned, the value for the whole of this pot from start to finish stays the same. That is what sets the cutoff frequency, and that's why it actually stays the same in our amplifier. I hope that clears a few things up. I still haven't really determined why we have that sudden onset of bass in the amplifier. To be honest with you, when I actually demoed it for you last time, it didn't seem quite as prominent as when I did it the first time. I think it's probably got a lot to do with the fact that what you have there is a big 12-inch speaker, or in the case of that demo, 2 big 12-inch speakers, and you have to get up to a certain power level before you can fully drive the speakers to get that bass frequency, and also you'll get the cabinet resonance and things like that coming in as well. So I think that's probably got a lot to do with it. I still want to experiment with capacitor values anyway. I should have really done the calculations before making this video, but I think off the top of my head, the cutoff frequency is still actually set at something like 160 Hz on that capacitor. So it still might be a little bit fun to play with, but ultimately I'm a little bit more confident that we can move forward and then kind of worry about these things later in the tone stack perhaps. Lots of things to play with. I don't, it is the first amplifier, so this is going to be something that we maybe learn about and improve over time. But it was certainly sounding acceptable, so we'll move on to the next task and leave it at that for now. So hopefully that's cleared a few things up for people. These videos aren't really meant to be educational in the sense that I'm going out there and saying I know how to do this, I know how to do that, this is how you should do it. This is very much about me learning how to do this for the first time. If people do learn things from my video, that is great, but I would always advise caution when trying to take something away from them, because chances are I'm doing it for the first time and I am likely to make mistakes like this one. In this case, it's not something that's lethal and going to set your house on fire, but you never know, it could be, which is why you should always consult some people that know what they're doing. Anyway, all that said, thanks once again to my mate Dave who pointed this out. Hope you enjoyed the video, and I'll see you next time.